questions from that quiz?
Oh, Marcus, Marcus Fierce.
Yeah.
Thank you.
Yeah.
Can you go over the velocity problem?
Yeah, so poor little dude. Not too bad. So if S of t is position, then velocity would be the change in S over the change in time, right? Is that decent so far? So if I want to know the average velocity from T1 to T2, that would be S of T2 minus S of T1 over T2 minus T1. So you really just had to use this 3 times over for those intervals I give you. Yeah. In the homework, the next step would have been make a guess to the instantaneous velocity, but I just didn't want to take it that far yet.
What's the cosecant 2 pi over 3?
Oh, okay, well, I mean, there were 4 different versions of the quiz. First off, some of you guys had secant, some of you guys had cosecant. All right, so of course, secant is the reciprocal function for cosine, right? S goes to C, C goes to S. That's the way to remember that. So this is going to be 1 over cosine. This is going to be 1 over sine. In general, I do want some kind of work, you know, especially since I let you use a calculator because I added that one problem on there. I need to see some kind of work. Well, you just throw this in the calculator. And the calculator passes, it goes to the next class. And then from here, you just have to figure out the reference angle, you know, so if you had, for example, let me do one that nobody had, like cotangent of 5 pi over 4. You could do 1 over tangent 5 pi over 4. What quadrant would this be in? Third quadrant, right? It's just a quarter of a pi past pi. So you could, and tangent in that quadrant is positive or negative? Positive. So this is equal to 1 over tangent of pi over 4. And then you can just attack that. All right, so you can do the same thing with secant. You rewrite it as 1 over cosine, or if you had cosecant, you rewrite it as 1 over sine. Figure out the reference angle. Is it positive or negative? Boil it down to a value you've got memorized. You're supposed to. I like it. Is that cool? Is that it? Okay. Anything else from there? Let's close this door up. Is everything else okay on that? Yeah. Oh.
Yes.
Good.
Do you want us making correctives on a separate sheet of paper or directly?
Cool. All right. So first off, don't change anything on the original. I want you to be able, and I want to be able to see what was wrong and then how you fixed it. You can do it on the back of the quiz, or you can do it on another sheet of paper. Either way, you turn in the new with the original. They're due on the day of the test. Quiz corrections and test corrections would always be due the day of the next test. And if you got an 80 or above, you can get 5 points back. Below an 80, you get a point for every 4 you missed. I think I already covered that yesterday. Yeah.
So if we do it on a different piece of paper, we only have to write down like the problems we're fixing, right? We don't have to like read.
Exactly. Yeah. Don't redo what was already right. In fact, if it was a long-ass problem and you made a mistake on the last step, start at the last good place and then fix what went wrong. Yeah.
For that problem, you put word question mark. So I'm guessing, because I already knew that, like sine of 5 pi over 6 is 1/2. I'm assuming in the future you want me to put the referencing to show that.
Yeah, just a little something. If I had not let you use calculators, I would have felt a lot better about no work being shown. You know what I mean? Yeah. What's going to probably happen for this first test is there'll be a part 1 and a part 2. And the part 1 will be no calculator, and the part 2 will be go ahead, use calculator. Yeah. Okay. Anything else from the quiz? So the average came out to be 74.3. 3 A's, 7 B's, 4 C's, 2 D's, 6 F's. The nice thing is if the problem is you just didn't do the homework yet, that's beautiful. That's the best. If you're going to make a low grade, that's the best reason to have, because then you can correct for that, right? If you're doing everything you can and you still made a very low grade, then you might want to come see me and see what's going on, right? The nice thing with the quizzes is you make those corrections. Quizzes are just, to me, they're just gauges saying this is where you should be. You better get ready if you ain't for the test, right? Okay, all right. And did I already tell you that, make corrections and you do better on the test? Yeah. I went over all that too. Okay. All right, if there's no more questions from the quiz, we're going to get right back into where we left off. Now remember, on Monday we have another quiz. Yeah. And if you're smart, you want more grades. So I already went over the whole nervous breakdown shit. I think, pretty much last time we covered a lot of the surface of 2728. So let's first remember what we did last time. So we started off, we kind of went along with the book. We're like, okay, book, we'll go along with you for points. We did the slope of a function at x equals a. So this unpackaged is the slope of f of x at x equals a. Which really means the direction that something would fly off in was following this track and suddenly came off, right? It's the slope of the tangent line at that point. I love it. It's also called the instantaneous rate of change, all that kind of business, right? What is the definition, the limit definition for this? It's got a limit in it, makes sense. Limit of, and let's do the main way, not the x goes to a way. Let's do the main way. H goes to 0. H, of course, is what's controlling what? What's H?
Yeah, how far
Yeah, so the point you're interested in, and of course algebra says, ooh, calculus, you're higher level than me, but you still need 2 freaking points. And calculus, okay, I just do limit shit, right? So H is just how far the other point is away from the point I'm really interested in, just to make algebra happy. And then we do the limit weirdness to get infinitely close to that, saying, it really is just 1 point, huh? So this is y2 minus y1. A plus h minus a would be x2 minus x1, and of course the a's cancel. All right, so that's the limit definition of the function. So when I say on a test or something, I say use the definition of derivative or slope to find the slope at 3 or something, then you have to do this process. Yes?
That's only going to be for the first test, right? And then we can like
Yes. Yeah. So some of you guys, I know some of you guys have done a little bit of calc similar before, and you already know like the shortcut rules for some stuff. You will be able to use that. Well, actually, to be honest, we're going to go through part of chapter 3, so part of that will be on this first test also. We are going to start looking at shortcut rules for certain things. Today we'll start looking at them.
Are we on track for the test on July 3rd or something?
No, the first test is
21st.
June 21st, yes, next Thursday, yeah. We are on track for that. Yeah. I don't know about the next one. We'll have to wait and see. Now this is 2-7. talks about this idea, right? Was there something else I want to say? Oh, and something that we're going to do over and over and over, so you go a little insane, is find the tangent line to a curve at a certain point. Once we get past the limit definition of derivative, we'll start talking about derivative rules for all kinds of different functions. And we'll learn it some here, and then we'll learn some more here, and then we'll learn some more here. And for each one of those sections, there will be a question: find the tangent line at the curve at the point blah, using the new derivative you just learned. Yay! So that process doesn't give a shit that it's different functions, right? So if I wanted to find tangent line to f of x at x equals to a. So for the equation of a line, I need two things. I need the slope. Well, what represents the slope up here? Where's the slope up here? Anything, where's the slope? What represents the slope? F prime of a, right? That's the slope. Oops. So F prime of a equals m. And you also need a point, x1, y1, which in this case would be a f of a. So just to show you, it's so easy to get lost in notation when in practice the shit is so simple. You know how to plug stuff into the y minus y1 equation. It doesn't really change. It's just that where we get the slope from is different than it was in algebra. Remember the questions, find the equation of a line that goes to the point 2, 7 and is perpendicular to this other line. Remember that question? So how do we find the slope there? It was perpendicular, so I had to do the negative reciprocal bullshit. So now I'm going to say find the slope, the equation of the tangent line to the curve at 2, 3. So now I've got a different way to find the slope. I find a derivative. But the rest of the process is the same. So what was the equation from algebra? It's this little dude. Plugging in calculus stuff, what does that look like now? Y minus f of a equals f prime of a x minus a. It's the same stupid thing though, right? You guys see? That just kind of is more in your face where stuff comes from, but it didn't change the idea at all. It's just that where we get the stuff from is different because we know more. Just in case you see this sucker floating around, it's that. They're the same thing. Okay. Now, let me ask you this. Let me make something more specific here. What if I had a situation where my function was like a profit function, so P is profit, and X is number of products sold. What would this, have I used that notation yet? That might be evil with me. No, okay, let me understand this. So P prime of X. There's slightly better notation for thinking about the meaning behind it more directly. What P prime of X, what is that in general? What is that? It's the derivative, slope of that profit function at any point X. And of course, slope itself is a rate of change. Slope is change in Y over change in X. So, do you remember how, so recall, slope used to be delta Y over delta X. Is that cool? I don't know, sometimes you'll see this symbol delta, most of the time you should, but some of you guys maybe never saw it. Did you guys see that symbol before? That symbol delta, Greek letter delta, just means change in. And normally it's considered a gross change in, like a big change, right? When I'm talking about limiting processes for finding the slope at a point, is that a big step? No. When I let h go to 0, how big of a step am I taking? Stupid small, right? What's called an infinitesimal. So another way to write this is the change in profit over the change in number of products sold, right? But I'm not going to use delta. That's a gross change. That's a big step. I'm going to use little d. That means it's an infinitesimal step. So that means the tiny step, the tiny change in profit divided by the tiny change in number of products sold. So what would the units be for P prime? Well, what units is profit? What do you, in the United States, are we having trouble about, well, you talking about Europe? Jeff? Are you talking about Russia? No. So profit is in dollars. I love it. So this would be dollars per number of products. I like it. All right, so if it was time versus value of car, we all know that graph goes like this. Time versus value of car, time in years, let's say, it would be dollars per year that your car's value goes down. Right? It would be negative, wouldn't it? I like it most of the time. Sometimes you buy an old car, you soup it up, and you actually take its value up. That's nice. Most of the time, no. Somebody with me so far? Do you see how this notation has an advantage over this one because number one, it shows you the units. It's these units over these units. Okay, that's great. That's in your face. But it also shows you exactly what you're taking the derivative with respect to. Prime sort of hides it. You got to know what the main variable is, especially when you get into multivariable calculus. We're currently in single variable, thank God. Okay. Let me see. Where do I want to go from there? I don't want to go to that one yet. Let's see. I got all that done. Okay. There's one other thing I want to say. I can't remember. Oh well. So section 2.8, we also did some of section 2.8. So section 2.7 really focuses on slope at a point. They use that point in the limiting process. And yesterday we talked about the fact that why don't I just create the slope function and then plug in whatever point I need? That's where section 2.8 comes in and says, oh yeah, we can do this. So section 2.8, the slight change in 2.8 is we say f prime of x. We actually get the slope function, the true derivative of that function. So then I can just plug in whatever point I'm interested in to get its slope there. And it's got the exact same idea here, except instead of a, I just use x, so I'm more general. Could be any point. But now we got to talk about, when we have a function, we can talk about where is the function continuous, where does the function exist. When f prime is its own function, so we can start talking about where's the derivative exist, right? Where's the derivative work? If I have, if my function looks like this, how is it? Yeah, I'll see that. Now I've kind of made it, there's a very interesting point there. So there is a definite, if this was a plane, I don't want to be in that plane right there. And this is an extreme, this is a cusp. Consider the slope, like here, what's the slope right here? What can you tell me about the slope right there? Positive. Here it looks to be 0, then it's a little negative, and then it's getting really, really big positive. right up until it gets to the point, and right on the other side of the point, it's really big negative. Would you say that the slope function, the derivative, is continuous through that point? Because on one side it's big positive, and on the other side it's big negative. So the slope does not exist there. F prime of x does not exist here. So let me call this point B. So f of x, the derivative, let me say it like this. Let me say it like this. Let me use the right word. F is differentiable everywhere except x equal to b. Or a little big F. So at B, this sucker is not differentiable. I'm kind of assuming this is going to follow this niceness. So that's one place where, that's one way that you can have a function that's not differentiable somewhere. Some more, so for example, there is a function that has this happen that's a little less funky, but we're very used to it. Say again?
Absolute value.
Absolute value. Absolute value, of course, says, yay, oh, it can't be negative, oh shit. So, of course, right there, again, another plane I don't want to be in. We're all dead. We're all dead. If you graph this, guys, then let me see if I can get you guys. Let's say this is just the straight up absolute value of x, right? Can somebody tell me what the slope is back here? Exactly what it is. Negative 1. Because what absolute value of x is x or negative x. So if I graph, in purple is f. If I graph the slope, what would it look like? It would look like this. It's 1. Oh, I'm sorry. Good job. Back here it's negative 1. And up here it's 1. And of course, right at 0, it does not exist. So see how the derivative itself would be not continuous through that point. So that's a point that is not differentiable. The function is not differentiable at that point.
So we're going to be like graphing like
Totally,
slope.
dude. And this is one of the first kind of things that your brain really rebels against. I have a handout we're going to do in a minute, in a little while. I give you a function and you've got to graph its slope on top. And what normally happens is students try to do what I say and then they just start following the function. Yay. Right? So what you got to realize is this is negative. So when I graph the slope, it's got to be down here. You're graphing the values of the slope. So this has got a negative slope, and in fact, why is this straight across? Because this slope don't change, right? But if I have one that's curvy, then this is going to get curvy. So don't worry, we'll do some together, and then I'm going to let you loose on some by yourself. Oh, okay. In fact, let's do some right now, since I came up. Oh yeah, real quick, there is 2 other ways for the slope to not exist at a point. There's this way, which is very straightforward. And then, of course, this one gets a little interesting. A good example of this is the curve x to the 1/3. Right here, the slope becomes infinite. So it's kind of mimicking continuity. You can have a jump, that's going to be a problem. You can have an infinite problem. This is the one that's reminding you that it's not continuity. This is talking about derivative. Is absolute value of x continuous through 0? You do it. What's it take to be continuous at a point? It's got to be approaching a value and it's got to get to the value. Well, aren't both of these approaching 0? And doesn't it get to 0? So is this continuous through 0? All day long. Why is it not differentiable at 0? Because if I try to graph the derivative function, it's not continuous there. That's one way to look at it. Okay, hopeful. Yes?
So it'd also be continuous through x 1/3.
Yeah, this is continuous also, exactly. But so it's this idea that the slope goes infinite. So it's kind of like analogous to our continuity stuff when we're thinking about where is it differentiable. So there is straight up jump. It's going to have no chance. Here it's continuous. The function is, but the derivative would go infinite there. That's a problem. And here this function is continuous, but the derivative would jump, right? Okay. Yes.
Why is it like a closed circle and an open circle?
Neither one of those are closed.
Oh,
Sorry.
okay.
Yeah, because right at 0, there is no slope. In fact, let me talk about that right now since I came up. For a normal function, for a well-behaved, for a function that's differentiable everywhere, if I take any point and I zoom in on it, what's going to happen? If I zoom in on this area, keep zooming in, what's going to happen? I zoom in and I zoom in and I zoom in, it's going to look straight. The exact same way that we are living on a curved sphere, but it looks flat to me, right? Because I am really zoomed in on this sucker. If the earth was much smaller, then we could be able to, oh, it is curved, right? Okay, much better than everything being made out of cobs. It's a small thing. So this idea of what's called local linearity. If it's differentiable at the point, if I zoom in enough, it will become straight. Now, why does that make complete sense? If it's differentiable, that means a slope exists. That means a tangent line exists. So there must be a point, if I zoom in enough, it's going to look like that tangent line would right there. So what happens if I zoom in on this point? Zoom in, it looks like this. Zoom in some more, it still looks like this. Zoom in some more, it still looks like this. It's going to look like that forever. I can't make it flatten out. In fact, if I try to, like here, you can say, you guys told me, that's 0 slope right there. No problem, because it sits right there really nicely. Now, if you push on this side, I'm going to go, whoa, but you can certainly put it on there and, okay, don't breathe. You try to do that, turn the sucker around, try to do that on him, pointy thing he is, no, right? It just isn't, it's a single point there. It's not going to be able to balance as well. Does that sort of make sense? That's another way to look at it. I don't like as much, but still. Okay. Okay. So we have the idea, and again, I've got a few handouts that captures a lot of what we just talked about. Let me try to do this one next thing with you and then give you this first handout. So let's do, what kind of function is this? Give me a guess. What kind of function is that? Like, is it a natural log? Is it a... You guys can do it. Can you? How many turning points are there? 2. So it's going to have to at least be degree 3. There you go. So more than likely, that's a cubic. It's possible at something higher level than that, but it doesn't seem to have any freakiness happening near the turning point. So it's more than likely something like x cubed. Now, it's probably going to be 4x cubed plus 0.7x squared minus 8x plus 2, because it's all wobbly and shit, right? You with me? But the end behavior is definitely cubish, right? Or at least odd powerish. Right, how are we doing so far? Okay, all right. So what I'm going to try to do right now, and what you're going to do later by yourself, is try to graph on top of this what f prime looks like. So we do this a couple times in mathematics. When you first learn logarithms, if it's done correctly, you graph it before you even know what the function is. Because you take an exponential and then you graph the inverse. And then you go, let's give this thing a name. Let's use the word log, because that's going to mess more people up. Yay. So here, what we're going to do is, I don't even know what the function is, but I can give a decent sketch of what the slope looks like, of what the f prime looks like. Does anybody have an idea? And again, some of you guys have taken a little bit of calculus already, so you know. where's like a good place to start? Where's some like, you just know for sure exactly what the value of the slope is? Where the slope is 0. That's my anchor points, right? I'm going to graph those first. So remember, what I'm about to do in purple is the values of the slope of this function. So trust me, I understand. When you start doing some of these, you're going to go a little insane. It's all about clicking it so you're looking at it correctly. But something to start off with is just find where the slope is 0. Plot those first, right? Since the slope is 0 there, then the purple line better go through that point. Let me take this away so you guys don't think that's part of the answer. So can somebody tell me the most important thing about the slope here? It's positive. Now the second most important thing is as I approach this, of course, it's becoming less and less positive, closer to 0. Are you with me? So exactly what we just said. It starts off decently big positive, becomes less positive until it hits 0. It starts off pretty big positive, becomes less positive until it hits 0. People try to connect the shape of these a little too much. The slope is positive, so I'm going to graph positive values, right? So if I estimate this slope to be 10, then this point better be a 10. Because I'm plotting the values of the slope. What happens after this point? Becomes negative. Can somebody tell me, there's a really interesting point right in the middle of these. Watch, it becomes negative and then it becomes even more negative. Are you with me?
Yeah.
But then over here, it becomes less negative. Somewhere in the middle there is where it is the most negative, right? You guys get that? Somewhere in the middle, there's a place where it's the most negative. Because doesn't it start to become more negative? And over here it becomes less negative. So somewhere in the middle, there better be a most negative slope place, right? That will become a very important point, not too far in our future. Right? But I estimate it to be, and let me just give you a little preview. Do you see how that seems to be what I would call cup down? And that looks to be cup up. This would hold water, this doesn't. Do you see how that relates to what the slope is doing? So they seem to connect somewhere maybe about right here. So maybe about right here is where it's the most negative. So watch what's going to happen. Is that getting more and more negative? And then somewhere right here, it's the most negative. And then what is it doing? Becoming less negative until it's 0 again, right? Stop right here. This is where you got to disconnect from this is kind of a weird thing to say. The shape of F matters and doesn't. What really matters is the slope that I'm talking about. All through here is negative. So see how all through here I am in the negative area, right? I have negative outputs. It's big negative, so it's getting bigger, bigger negative, and then it's getting less and less and less negative until it's 0 there. Bam. And what's it doing after this forever? Getting bigger and bigger and bigger positive. Now look what is that purple graph? Yeah, it's like x squared. So f prime is like x squared. And that's going to be one of our first shortcut rules, is how to do derivatives of powers of x. So an x cubed becomes somehow related to an x squared. An x to the 4th would become related to an x cubed, so forth. In fact, let's do one more, and then I'll let you guys try a few on your own. Let's start off with an x to the 4th. Anybody remember what x to the 4th looks like? Or more generally, it could look like a parabola, but more generally, what would one look like? And you guys are all like, what the shit? I don't know. I didn't take my math biology class. Here's what one would look like. Affectionately known as the butt graph by some of my students. There's a better butt graph about the cardioid. I can't remember. Did you guys do cardioids, parametric stuff in 176 and pre-calc? No? That's too bad. Anyway. This could also be a few other things, but we'll leave it alone. So this is F, and now we're about to graph F prime. So somebody help me out. What's true about, what am I thinking about as I look at this, about to graph the purple one? What am I thinking about? I'm looking at the slope. And so where should I start?
Negative.
Well, no.
Below the x-axis.
I should find what points the,
0.
yeah, where it's 0. So this is a big negative. Now 0 right there. So about right there. What else is a 0? Yeah, about right here, roughly. And then right there again, roughly, right? So those are your anchor points. Those are ones that will have horizontal tangent lines. In general, do you see how that would be something that businesses and so forth and anybody trying to optimize things would be curious about, because the optimization of stuff always involves like the peak or the valley, right? The minimum material needed, the maximum profit, right? So finding where the horizontal tangent lines are becomes a very important process, because very often that's where your best place of being is. Maximum profit, for example. So this is big negative. So but people try to, they kind of start following this thing. It's not positive slope, this is negative slope. So it should be down here. And of course the slope is getting less and less negative. So that's why I am going to start to approach this. Now what's it do after this? It's positive, right? And in fact, again, isn't there going to be somewhere in here a most positive? Because after this, it goes to 0 again, right? So there's going to be a most positive, so maybe about right here, and then it goes to 0 again. And here's why people have trouble with this, because sometimes this will happen. What's happening after this? What's happening here? It's negative. So this is where people just sort of start following it, right? And I don't blame you, because it's kind of like the purple gets on the track and you just go, wee. But you got to remind yourself, again, what's the point in here that's curious is like the most negative. So that should be the turning point of the purple. If it's most negative, then it shouldn't go any more negative than that. So this should be about right here maybe, and then it turns to go back through this. And of course, after this point, it's getting bigger, positive. So there's a good, this was x to the 4th, roughly, and this looks like a cubish. It's not a proof, but it sure is damn good evidence that the derivative of a 4th power looks to be a cube somehow. I like it. So here, let me give you guys this. Oh, is that one coming later? Oh, let's do this. Let's start with that one. And then I give you this other one. I'll give you these out of order a little bit. This is graphs related to what we just did. So try to do this side here with all the graphs on it. The other side is chapter 3, so maybe don't look at that yet. So do the side with all the graphs on it.